This conference will now be recorded.
Once again, thank you for attending this webinar on system level modeling for performance and power analysis using Visual Sim. Okay, so during this webinar, we'll walk you through the need of architecture explorations and what are the challenges which are faced during the modeling. We'll brief you about the SLM and we'll give you a demo and construct a model in between. We'll walk you through about what is Visual Sim and how we can design our model or a design on it, the application and the libraries. Then we'll discuss about different types of models, stochastic braking system using ISO 26262. Moving on, so the first case that arises, what is the need of architecture exploration? So the main motive of this webinar is to understand the need of it. So let's take an example. Let's say you have a block diagram design and you have to proceed to the next stage. So normally what happens is verification of the design is done at RTL level. If we find any fault in the design at that point, then we have to come back and recalibrate the design, which is going to take a lot of time. So at the end, which will result in a lot of resources and time being wasted by going back and forth. So all these scenarios can be avoided if system level verification of the design has been done prior to the development. There are 4 points that are listed here on the slide. So before a development, you can identify the bottlenecks, the cases in which your design may fail. Then if we talk about the architecture exploration, the buses, which bus should be used, how fast should the bus be, and how many processor we can use, or if we are doing hardware software partitioning, then what can be done in software, what can be done in hardware, will partitioning change in future iterations? All these questions can be used, and because of all these, we need the architecture exploration. Okay, so the challenges that we face in our modeling, there are various challenges like if the absence of GUI, limited functionality, timing, time consuming, and then inaccuracy. So a spreadsheet is mentioned here, and we can see that it is most of the time it is inaccurate. So suppose a system modeling is not in your current methodology and not a priority because it takes too much time. So we provide an infrastructure that with training can be an ongoing activity. It is no longer a one-time activity. It increases the productivity of your engineers because they do not have to spend their time doing the same work again and again. They have a method to identify the errors and bottlenecks. So here I'm going to talk about a little bit uh, about the Visual Sim. So Visual Sim provide the extensive libraries. So you do not need to learn the protocol before replacing a PCIe with a USB 5.0 because we have a library for that. Statistic. Statistic to calculate uh, reports quickly. We can make decisions. So there was a kind of a disturbance. Excuse for the disturbance. Okay, so yeah, so we can calculate the statistic based on whatever design you have. You can analyze it on our tool, and then the infrastructure to quickly debug and make the model look like your block diagram. So before we move on, okay, scorecard. So let's talk about the scorecard by taking an example. The scorecard first comes as animation, then listen to code, listen to block, tracer, diagnostic. So suppose we take an example, a basic example for this model. A basic model which is having two queues, a traffic block with different parameters, the expression list in which I have defined some values. There are two queues. So what I'm going to show you here is the traffic will be generated and will pass to the queue. Till the queue get filled, um, until the queue get filled, it will pop the packet out of the queue and then it will work as the input for the second queue. As you can see here, input, the type general for the Q2. And then you can see the result. So I will run this model for one time. So we can see here the different the statistic that is being generated from the resource stats, and you from here you can see the occupancy, the packets rejected, the packets entered, exited, and what is the utilization for particular interval of time. Now here you can see the packets which came out of the queue. Now the main purpose here is to show you that we talked here about the listen to port animation. Okay, let's see animation first. Suppose I'm for 250 milliseconds, this animation will work, and we'll see how what is the sequence, what is the flow of this model. So this is the flow that we have seen here. It is going from traffic to expression list to the queue, and it is filling the queue the till the queue reach its length, which I have defined here as 30. So 30 packets will be filled in each queue, and then popping will start from here. From this constant, will pop each time whenever we get an input at the constant, will pop the packet out. Now, here a very interesting block called diagnostic is present. In diagnostic, there is three parameters. We only worry about the two, the statistic file and the write stats to file. The statistic file it is a user's file, so user can create a file and they can give the CSV file here. So suppose you are running a model and you want to see that how many packets are getting out of the queue which are having latencies greater to some specific value. Suppose the latency is greater than 2. So let me show you a file. Yeah. So here a very simple file which contain only one okay. smart resource, the name of the queue block, then the start name, the constraint, and the value. So suppose I want that my queue, whatever packet should come, they should be greater than 2. Their latency should be greater than 2. So I will run this model for 60 seconds and we'll see the result. So the file will be created wherever your model is saved. My file gets created here and I can see the different stats for utilization. For queue utilization will be 0. Then at what time each packet coming out, which is having its latency is greater than 2. So all the latencies for each packet, whichever is greater than 2, will be shown into this CSV file. So this is buffer occupancy. Buffer occupancy means in the queue, I have mentioned that the number of queues should be three. Uh, Sorry, the number of queues should be 3. So for so then the length of each queue will be 30 because I have measured it there in the parameter. So now the buffer capacity will always be same. It will always be full, and we can see here that what is the buffer capacity. This is buffer occupancy. So what is the buffer occupancy at each instant of time? So as you can see here, the first queue is getting popped up like 33432 is getting popped up, so it is not getting filled up that much. But as you can see, as the time passes, the Q2 and Q3 is getting filled up more because it is not getting because no packet is getting popped up from the Q2 or Q3. So this was about the diagnostic block. Now listen to port and listen to block is another interesting feature to debug if is something wrong with the result, if you're not getting any packet out of the queue or any other block. So we have a library here, as you can see at the left hand side. We have a library. From here, I took this queue. I just drag and drop the queue and I can use it. So, yeah. So, suppose I want to listen to port, and at the same time, I want to see what is happening in the expression list. So, I will right click on it and I will listen to block. So, if I run this model, I can see the expression list and the input queue. So, if I go on the top, I can see at what time the first packet came in and what is the ID of each packet, what is the uh, at what time it came in. At the same time, the input port of the queue first. Here, this one. Listen to port. So here at 1 second, uh, ID2 came, and before that ID1 came, and likewise we can see at each second some packet is being sent inside the queue. So this is all about listen to port and listen to block, which is available in the Visual Sim. This is a basic layout, this is a basic UI of our tool, and yeah, let's proceed. And the tracer is basically the text display that you can see here. You can trace all the packets ID and the stats and analyze the result. So let's talk about the modeling. Let's have a basic definition of um, of uh, of what we are analyzing with regards to what we are analyzing. So the architecture exploration is a key term here, and uh, I will be talking about the specification. Suppose that you have some specification and you want that you have developed that you have developed either on paper or PowerPoint or Excel, and assemble a model such that as you can see at the right hand side, this green color model, you have assembled it. And so what we are going to do is we will run a variety of simulation on this, where you can vary your processor speed, bus topology, you can put different algorithm, round robin versus FCFS. You can analyze how your model work, how your design will work for both the algorithms or different types of algorithm, and then you can evaluate the timing, energy, the cost, and the weight on your design on your particular design. So all these are attribute to come up with an optimal specification. Let's talk about the performance analysis, the power measurement, and failure analysis. So performance is more time related. So it can be buffer size or end-to-end latency, sorry, end-to-end delay, the throughput. The power is it is more focused upon how much power is being consumed per task, or power uh, or device, or even looking at spikes in terms of certain shocks. Function is about which scheduling algorithm you are using for your design for your system. And failure analysis is about analyzing the data, determining the fault, and finding the corrective solution, which is very important because every design will have some bottleneck, some loophole which needs to be analyzed, determined, and then find a corrective solution so that your design can be made more optimal. Now, design exploration. So this slide describes various cases where architectural design exploration has been done. So it can be on, suppose, how many tasks can I add to the system, or do I partition across a multi-core or multi-processor, or which algorithm should be used so that I can meet the performance. And then the power consumption, how much your design is consuming the power, or what are the ways that power can be reduced. This is all just to make the model more optimal for use for use. Okay, a quick introduction about the company. We the company name is of course Mirabilis Design, and we have been around for about 15 years. We have got development and support center in multiple locations around the world, and we have got 40 customer in a variety of application. Here you can see all the companies we have been linked up with, and the product is Visual Sim. I already gave you a demo on the Visual Sim, which is a modeling and simulation software, and it comes with a complete package of modeling IP, analysis tool, simulators, and post-processing environment that allow you to do your architecture simulation. So the company itself is made up of system architects and the folks that have experiences in performance modeling. Moving on, the application of visual sim. So, as I have already mm, um, described the model, which was having two queues. Now, the application of visual sim is yeah. So there are like three main areas, that is hardware, software, and network, and and the analysis around it is performance analysis, power exploration, hardware software partitioning, and failure analysis. So the whole goal of the system is to be able to construct a model in a graphical manner, in a graphical environment, using predefined libraries, and then run Monte Carlo simulation with variety of traffic use case parameter, and then be able to analyze the result, right? Okay, so let me ask you a question. Why is Visual Sim preferred in the market? So the reason is because of its extensive libraries that we provide. So if we look from left to right, it starts from more stochastic stochastic transaction level modeling, and if you go towards middle, you will see more system, network, and finally more detail. Cycle accurate model. So a tool cover entire IPs and tech that is required for you to assemble your system. The type of analysis. So a variety of analysis that can be done using our tool is listed here. Performance, in performance, we can analyze the latencies, throughput, and utilization. So latency is basically the time taken for the task to complete. The throughput is the rate of data transfer, and utilization is how much resource has been utilized. And then power, we have already talked about the power. There are like four key features that we have already covered, like power, how power should be reduced, what is the consumption of your power consumption of your design, or if there is a deadlock present in your design. So all these analysis can be done on this tool. So here is a very interesting plot which consists of two speeds, bus speed, which is one is 200 megahertz and 400 megahertz. So yeah, so it is expected that 400 megahertz bus will run more faster, and so the latency will be much lower for about 50 to 20%. Now, here is a scenario. As you can see here at the circles, we can see there is a spikes of the latencies for this bus. So this is happening because okay, let's consider this scenario. We have a lot of processors and DSP, and buses are faster, so they are pushing more data into the processor. So which in fact is allowing processor to start buffering, which as a result resulting in more delay, which is spiking up over the time. So we can see here there is a spike at 4 position for the bus with a higher speed. Okay, another interesting example for the power analysis is how accurate is our tool, is visual sim. So there was this one model uh, in which the power, given power has to be generated, and then by going back and forth we generated the power at 1.19, which was exactly the same which what was what was needed in the stat. As you can see, we specified 1.19 here at the red circle, and this is exactly what we got when we plotted it in our latency plots. So here, so what is happening in this software task scheduling? It is basically defining that there are three tasks, and we will talk first about the task three. That task three started here at this place, and then it was expected to complete between 100 to 200 seconds or units, but it got completed at 300 seconds. So why was it? Because the higher priority task came in, and the higher priority task, as you can see, T1 and T2 came in, and so that task 3, T3 has to wait. It was on hold till the task 1 and task 2 got completed, and then task 3 get executed, and it got ended around 300 seconds. So these are the task deadline, which is really important when you deal with some RTOS RTOS system, real time operating system, where we need the real time deadline. We need the task to be completed within that deadline, within its execution time. And all these things can be analyzed. Okay, before we move further, let's build a simple stochastic model. So let's take first a digital simulator. Okay, digital simulator. And the traffic result to plot the latencies, then expression list to vary the input fields, data structure field, and the resources. Let's take server. So I'm just connecting one port. I just drag and drop the blocks, and I'm connecting one traffic block to another, and one to another. I connect expression list to server. I need one more expression list to plot the latency. So here I'm going to modify some values. I'm going to type latency is equal to my T now minus input, sorry, input on time. And here I'm going to pass latency. Now let's give it some time, like 0.5. Yeah, and then traffic. Okay, in this traffic block, there is a time distribution parameter which consists of single event, fixed event. So single event means only one time the transaction will be sent out of the traffic. Fixed value, till the end of the simulation time, the packets will be sent out of the queue. So sorry, from the traffic. So I will choose fixed value, and all this will be same. Here in the digital simulator, when I double click it, I have to specify a stop time, otherwise it will throw an error. That is, stop time cannot be infinity. Now, and here I have specified the time. So for how much time the packet will get processed inside the server. So so we got a linear graph. Let's make it more interesting. Let's make it 0.5 milliseconds. And we can see some spikes. About all these packets, the 10 packets came, and we can see how the latencies of each packet changes over time. Let's plot stats also. So we go in, yeah, resource statistic, and then the text display. Here I have to, inside the resource statistic, I have to mention the name of the block which I want the stats from. Here I am mentioning the name of a server block, which is my time resource. I want the number of samples 2 and resource length is 3. Mm, Okay, so we got some error here. Let's see what is the error. Oh, it's saying model has to be saved. So let's save the model quickly. Okay, yeah, required model has to be saved. Yeah, and this is the stats for the server. So the stats will contain the number entered, number excited, number rejected, and the occupancy, the buffer occupancy, and the utilization basically. How much of a resource is getting utilized. From here, you can see only two stats came. Now, this is a very simple stochastic model. Let's make a cyclic model. So with the cyclic rate, I need um, AXI bus, just here. I will remove the server. I will move this here. And I need a memory. We'll connect memory. And then I need a device interface. If you get lost somewhere, you can just type the name, and yes, it will do the rest. So device interface, and we don't need this now. We need architecture setup and results. Let's make some quick change. The name of the memory is SDRAM1 and the type is SDR. We are going to give the name over here, that device attached to slave by port. We have to mention so that the packet don't get lost. You don't have to search for the destination. And so yeah, SDRAM1, all good here. Then you can give a name here for the IO device. Suppose I'm giving here 1 and I'm changing this name to SDRAM1 IO destination. Let's see. Oh, so we got another error and say incoming data structure does not contain one or more necessary field. So I forgot to change the data structure. Here the data structure name is header, which contain much lesser field. I'm going to put it as processor DS. Let's see. Yeah. Okay. So this is what we got for the cycle upgrade. And the architecture setup is basically used to generate the stats for the bus and for the memory. So here you can see the stats from the memory which are coming in from the architecture setup, that the delay time max, mean, and then the throughput, the memory used, by total memory used by the total system, memory used by the IO interface. All these things can be analyzed using our tool. So this is a simple cycle rate, and if you have any error, or you stuck with some error, or you think that how memory is working, how the data is being sent to the memory, we can just listen to code here. Click on listen to code and run the model while that window panel being open, and then you can see the result. So let's get back to the presentation. Yeah, so stochastic modeling, bus architecture. So in this, we have a number of input channels, and basically here what you're looking for is two system, ingress system and egress system. So and one of them has a large number of channel, which all are channel all have an individual buffer, and all of which will arrive at intermediate channel here that feed into the another single set of channel, that is egress channel or egress queue. Now the key thing here is to maintain a credit as a flow control. So between both the system here and this one. So, and to ensure that the drain time is always greater than or equal to the input time. So if I look at this design here, we have the same replica of this prototype on our system here. The same thing. We have two ingress queue and we have two ingress queue. We have egress queue, the out queue. We have exon queue, exoff queue, and when I run, we have traffic, and then expression list is there. Script block is there, which consists of some algorithm. I would say it is round robin and deficit round robin, as you can see here. And then if I run this model, we have defined a threshold for the egress queue so that the packet can only be sent out from the ingress if the current capacity of the here. So if the current capacity of the egress queue is less than the threshold, there's a parameter called threshold. I will show you. So here you can see the latency is increasing as we go further. So here's the spikes there in the latency. Okay, yeah. So which we can see from here in our histogram, what is at what time, at which point it is. See, you can see here at after 1.0, we can see the spikes in the latency, and then it is all very small. So yeah, so the main point was in this flow diagram was if the current capacity of the egress queue, this queue, is less than the threshold. Here we have defined a parameter called threshold. So also we have here two scheduling algorithm called round robin and deficit round robin. If you pull down this, we can see the menu and we can change it. So the packet can only be sent out if from the ingress from the input queue if the current capacity is less than the threshold. So this was the whole situation, and we have replicated the whole design, which was here on our model, on our system model, on our visual sim. So let's get back. Now this is the same model that I have shown you. Second ago, minutes ago. Now, the very interesting topic called variant analysis, which is, I already explained, it is very important because every design will at some time it will incur some type of failures. So here what we are looking for different kinds of failure at hardware level, software, RDOS, power, and network. As you can see at the right side of my screen, there are the image, there are three tasks, A, B, and C. And as you can see, task A is holding resource 1, B is holding resource 2, and C is holding resource 3. And A is waiting for resource 2, B is waiting for 3, C is waiting for 1. So this is a condition for a deadlock, which occurs in a software failure. And then as you can see at the lower bottom image, at the right hand side, there are two nodes that was that is of red color. This is like initial node failure. So initially two nodes in a network, in a whole network, two nodes got failed. So suddenly those two, whenever the correct data will come to the failure node, they will send the incorrect data, and then this will become a chain, and there will be connectivity failure, dependency failure, and then we can see again the connectivity failure over here. So the wrong data will be transferred across the network. Now, hardware failure is more like a loss of codes and limited storage. The software failure is more about the memory, the deadlock that I explained, and like inconsistent data, which we can see when we talk about the database, where there are two datas trying to get for one object, or like if there is one input, two data trying to write values or read the or maybe doing some work on that. So we can see that for the software failure, inconsistent data and then deadlock is mm, more of a failure. Then in a network failure, the most common is the network failure, where you don't receive the data, or sensors are not providing data fast enough. So in worst case, you might have sensors sending incorrect data, which we have seen that if nodes get failed, and it will send the incorrect data. So power failure already explained before that if you lose a power, you have to slow down some processing, or you actually have to limit it yourself for like number of resources. And a, a perfect example is like satellite. So a satellite system where we are not facing the sun, as a result, battery is not getting charged up. So the RDOS failure is when the task execute task takes the time to execute more than its execution time. So that is unable. So in that case, task is unable to achieve the real time deadline, which is very important in auto. If we talk about automotives and where the real time data is needed. Yeah. So these are a basic failure that can happen in this uh, sections. Moving on to our braking system. So there's a model called braking system of a car. So basically, we all these failures that I've mentioned here have been integrated in this braking model. So let me show you. Yeah, this is a model, and it is having like four wheels, couple of sensors, road condition sensor, proximity sensor. Then there is a gyro sensor. Brake is there. Here is brake is there, and then what each block is doing is each block is feeding the data to the ECU. Okay, so Yeah, so each block is is feeding the data into the ECU. So if I run this model, I can see a variety of, yeah, I can see a break latency. So whenever the break is applied, we can see the latencies of the task, then the average power which is being utilized. This is a very interesting stats. You can see here for different load condition we have the correct data. So if at a real time, if some wheel is not getting the correct data, we'll send back the data. We'll get the correct data at that instant of time. Suppose if the road condition is varied from like it's a rough road or icy road or a gravel road. So at what time we are getting the data, correct data if the brake is applied. So all these things are specified in this. Yeah, this this plot is basically specific to RTOS failure. So we have three slots, slot 1, 2, and 3, and we can see that the slot 2 here, yeah, slot 2, yeah. So you can see here there's a time gap between between a task in the slot 2. So what is happening here is why there's a gap between these two tasks here and in this, because maybe the task that came in that slot got executed for more than the threshold, and it might have exceeded the execution time. So if there is any task, if for a slot, if a task came in the slot and it got executed more than its execution time, and it happened for like 5 6 times, we will shut down the whole slot, we will restart it again after some time. Here's a threshold for that thing. Here's a slot time for all the three slots. So likewise, okay. So likewise, we can identify which where the task, there is a loophole is where the task is getting executed more than its execution time. Now, yeah, moving on to the end, we can see a software modeling. So the flow diagram is already being explained how the flow works from traffic to expression to the queue. The instruction sequences basically specify the sequence of instructions through which tasks should follow. We also have integrated Gem5 to a tool. We can run operating system and software on Gem5 or a piece of board on Gem5 and rest of it on Visual Sim, so that we cover the end-to-end system fully. Here is the integration between the Gem5 and the Visual Sim. So what happened is, let me explain you what happened is, from Visual Sim, whenever we want to use a module implemented in Gem5, we trigger the Gem5 wrapper and integrate which is integrated in Visual Sim. This in turn kicks off the Gem5 execution. So after Gem5 finishes its execution, the data obtained from Gem5 is used in the later stages implemented in Visual Sim. So this is a basic layout here, the connection between the Gem5 and the Visual Sim. So moving on, the custom function in Visual Sim. So there are like uh, number of custom function that can be used in Visual Sim. Suppose script block is the one that I have already shown you, which was having a round robin algorithm and other algorithm, which can be which user can write just for the custom functionality. Then we offer system C, Verilog, and you can write your C++ code also. And all these things are already integrated in our library blocks. Okay, so if you have any questions, you can ask.